You think it's all a ploy? We're recording now, so be careful of what you say. Don't want the FBI coming after you or something. Oh, let's see. Got blackboards here. All right. So we're talking about FM now in this chapter. And so we're comparing our different modulation systems. And so our couple things that we're comparing as we look at each of these is certainly the power consumption. Okay. Because that's of concern, for both the transmitter and receiver. Also the bandwidth. Okay. So given a certain spectrum, how many channels can we put in that spectrum? That depends on the bandwidth of the signal. Another thing that we'll be concerned about is the fidelity, how good it sounds, and that's a function of the signal noise ratio. That's actually something we just touch on a little in this class because we don't really have a good characterization for noise. At the undergraduate level, it's usually reserved for graduate classes and Fourier transforms of noise or study of random processes. So we'll talk a little bit about that, but we don't get too deep into that. But primarily here at this point, we're characterizing our different modulation methods, comparing them based on power and then bandwidth. Now for AM, bandwidth was really pretty simple. It was either the bandwidth of the baseband message or twice that. Power was a little bit more complicated. For AM, it depends on the modulation index, and we had the sideband components as well as the carrier component. FM, power is really easy because the amplitude doesn't change, right? It was just 1/2 AC squared. That's the power for FM. It's the bandwidth that's much harder to figure out for FM. So we have to make some approximations and look at some simple cases when we're considering FM. We'll look at what's called narrowband FM today, and then we'll look at wideband FM on Monday. Okay. So whether it's narrowband FM or wideband FM depends on the range of instantaneous frequencies. So last time we had for our FM modulated carrier, we had this expression for both FM and phase modulation. But for FM, we said that the instantaneous phase is proportional to the integral of the message. In phase modulation, the instantaneous phase is directly proportional to the message. And the instantaneous frequency remember is defined as the time derivative of the instantaneous phase divided by 2 pi. So that's FC plus KF MT, okay, is the instantaneous frequency. So now typically, we assume our message is, varies between, plus or minus 1, plus or minus 4, or whatever. It doesn't really matter because of this multiplication constant here. But we assume it goes both positive and negative by an equal amount. So often we assume it's normalized so that it goes between plus or minus 1. So that means that the instantaneous frequencies would go to FC plus KF would be the highest frequency, and FC minus KF would be the lowest frequency. So you know, at first glance, you might think, well, that means it has a bandwidth that's just 2 kF, right? Because that's the range of instantaneous frequencies. And so by making kF small, I can get a really small bandwidth. Okay, well, that turns out to not quite be true, because the range of instantaneous frequencies is not the same as the Fourier transform of the original carrier. And so this was misunderstood for, a long time. Radio's been around all your life, even all my life, believe it or not, but it's been around for a long time. But it really, FM wasn't probably understood, theoretically until the 1940s or 1950s. Because a lot of the engineers at the time said, oh, it's got a bandwidth of 2 kF, and actually doing measurements, that turned out not to be true. Something else is going on. And again, we have to look at the Fourier transform to really figure out the bandwidth. It's different than this. Now, this is a portion of it, okay, but there's another component that determines the bandwidth. Okay, so and we need to take the Fourier transform of this, or this plugged into that. It's not easy to do. As a matter of fact, it's a problem that hasn't been solved in general for an arbitrary message. Okay, so we have to look at some simple cases. So we're going to look at the tone modulation case first, and we'll even further reduce it and look at tone modulation with narrowband FM. And then next week we'll look at tone modulation with what's called the wideband case. So there's another set of approximations coming up here in just a second, even with this simplification. So with tone modulation, the message is just a pure sinusoid. So it's not voice. If you would just hear a tone if you transmitted this, a pure, FM here might be a kilohertz or something like that. At the FM receiver, you'd hear a 1 kilohertz tone. Okay, but it's the simplest type of message that you might imagine. We can have it with AM as well. We talked about the tone modulation case, but it is something that you can hear. It's a nice test signal, in the lab or in the field, but it's also nice because we can deal with it theoretically and at least compare this to the bandwidth for AM. So the instantaneous frequency then is FC plus KF AM cosine of 2 pi FM of t. Okay. Or FC plus delta F cosine of 2 pi FM t, where delta F is KF times, whatever our FM modulation constant is, that KF times the amplitude of our tone. And again, the instantaneous frequency goes delta F above, delta F below. It appears that this thing might have a bandwidth of 2 delta F. Okay, so FC minus delta F is less than the instantaneous frequency, which is less than FC plus delta F. Okay. Now, let's take this a little further and look at the instantaneous phase, because that's what we need to look at to start talking about the Fourier transform of this thing. Okay. Now, because this is just a tone, we can integrate it. Okay. I started with a cosine, so I'm going to get 2 pi FM sine of 2 pi FM of t, right? Integrated cosine of 2 pi FM of t with respect to at time, I divide by the 2 pi FM, and the cosine becomes the sine. Then the instantaneous phase is 2 pi FC of t plus delta F over my tone frequency, sine of 2 pi FM of t. Okay. So anytime engineers see like a ratio of constants, they like to immediately define a new constant. So we rewrite this as 2 pi FC of t plus beta sine of 2 pi FM of t. Because in what follows, delta F, it's that delta FM over FM ratio that always appears. And so that just for notational convenience, that's defined as beta. So where beta is delta F over FM. And this is what's actually called the FM modulation index, is the FM modulation index. Okay. It's the ratio of the peak frequency deviation to the tone frequency. Okay, so going back to, we can write our carrier now as AC cosine of 2 pi FC of t plus beta sine of 2 pi FM of t. Okay. Well, I don't know how to take the Fourier transform of this either. Okay. It's simpler than having the integral of MT in here, you know, with the tone modulation case, but this isn't in any of your tables transforms. Okay. So well, let's see if we can simplify it a bit more. So using cosine of A plus B is cosine of A times cosine of B minus sine of A, sine of B. I get AC cosine of 2 pi FC of t cosine of beta sine of 2 pi FM of t minus AC sine of 2 pi FC of t sine of beta sine of 2 pi FM of t. And it appears maybe I've made the situation just worse, certainly longer. Okay. But, you know, at least I know what multiplying by a cosine does to, you know, if I knew the spectrum of this, I know what multiplying by a cosine does, right? It just shifts the spectrum up plus or minus FC. So does multiplying by the sine, just shifts the spectrum up plus or minus FC. And the problem is now I don't know the spectrum of this, so the Fourier transform of this. It's not in any sort of table. But you can stand back and say, well, is there some sort of approximation that, you know, maybe for small or large beta? Okay. And if beta is small enough, cosine of 0 is approximately 1, right? If I can make beta small enough so that this is close to 0, cosine of 0 is about 1. Okay. Now, do you remember another common approximation that you run into in calculus and engineering, especially communication, is sine of theta for theta small. Do you know what sine of theta for theta small is approximately? It's approximately theta. You know, in radians, the sine of theta is approximately theta. So again, if we restrict ourselves, at least now, for the small beta case, and this is what corresponds to what we call narrowband FM, we can do another simplification. It's not going to be true in general. It's not true for large beta. We'll tack that next time, but let's talk about this small beta case. So for narrowband FM, we assume beta is much, much less than 1 in radians. Okay. And we would like the general result, but we're not there yet. So let's take a look at this and see if we can do anything from it. Hope something works out. And there are some radio stations that transmit narrowband FM, as in particular, I think the Naval Observatory, they send out a weather signal that's narrowband FM. So it is in use. So with this approximation, cosine of beta, sine of 2 pi FM of t is approximately 1, and sine of beta, sine of 2 pi FM of t is approximately the angle, beta sine of 2 pi FM of t. Okay. So we now have, with a couple of simplifications, tone modulation being the first one we made, and then now we're making this restriction on a small beta. We've got an expression for our FM carrier. It's AC cosine of 2 pi FC of t, which is just an impulse, okay, minus beta AC sine of 2 pi FM of t sine of 2 pi FC of t. Okay. So what do we have now? Now, actually, I've got something. I could draw the spectrum, and I could draw the spectrum here. This is an impulse at FC. This is the spectrum of of a tone at our tone frequency. So it'd be a pair of impulses at plus or minus FM, modulated up to FC. Okay. So we got, an impulse, and then here, this is going to produce terms at FC plus FM and FC minus FM. I mean, we've looked at this in the past with 2 cosines, right? And 2 cosines gives us the sum and difference frequencies. Sines are just 90-degree phase shifted cosines, okay? Product of 2 sines gives us exactly the same result. We'll get sum and difference frequencies there. So we have an impulse at FC, and then impulses on either side of that at FC minus FM and FC plus FM. That's AM radio, okay, essentially. It has the same, it's different, but it has impulses at the same locations as AM radio. Okay. So we'll come back and talk about that in just a second, but let me talk about how to actually generate this first. This is equal to, so now I'm going to go back and substitute in my message. It's AC cosine of 2 pi FC of t minus AC sine of 2 pi FC of t. And if you look at where this term came from, the sine 2 pi FM, it was 2 pi kf integral of my message signal. Okay. So it suggests the following narrowband FM implementation. So we have our message coming in. We multiply by 2 pi kf and integrate. Okay. That would actually generate, that's this term. We multiply by sine. Okay, so actually I have a generator here that generates a cosine 2 pi fc of t. Okay, and I shift that cosine by 90 degrees. A narrowband phase shifter only has to shift at that one frequency to get the sine term. Okay, so I multiply those two together, and then I just add in my cosine. This term is actually subtracted. And it suggests this as, a block diagram to create this particular signal. Now, I have no idea yet how to actually recover our message, from this. We'll have to figure that out. But this is a narrowband FM modulator. We'll see that this is often a component of what's called a wideband FM modulator. So even though wideband FM is used more in practice, one way to generate wideband FM is to first generate narrowband FM and then do frequency multiplication, which we'll talk about. Frequency multiplication is not the same as mixing. So let's go back and look at the spectrum a little bit more. So the narrowband FM signal has the form of a narrowband signal. Now, we talked about narrowband signal representations only briefly in a previous chapter, but any narrowband signal can be represented as what we call the in-phase term multiplied by cosine 2 pi fc of t minus the quadrature term times the sine. Okay, and this was true for standard AM radio, where you didn't even have the quadrature signal. Okay, you just had the in-phase term that was, 1 plus the message, the message with a DC offset. And it was true for double sideband, again, where you didn't have this. But it was also true for what we called the quadrature AMs, which had both of them. And it's actually a general representation for any sort of narrowband signal. We can actually use it even for wideband FM. But it certainly applies, and we can see it here in narrowband FM, where our SI term would just be 1, and then our SQ term would be AC times the integral of our message. Okay. So where SI of t, well, it's actually AC, and the quadrature component is 2 pi kf AC integral of our message. Okay. So in the amplitude phase representation of the narrowband signal, that's yet another narrowband representation that's related to this one. It's called the quadrature representation. We have AT cosine of 2 pi fc of t plus phi of t, where this thing looks, this looks like a general modulation signal, right? If AT is varying and we have no phase angle, we've got amplitude modulation. If this is fixed and this is varying, then we've got either phase modulation or frequency modulation. So little AC here is the square root of the sum of the squares of our in phase and quadrature components. SQ squared of t to the 1/2. And the phase angle is the inverse tangent of the quadrature component over the in phase component. This is really just kind of like the phasor representation of this thing, but with time varying components here for the amplitudes of the in phase of what we would take to be the real and imaginary parts of the signal. The signal here, based on a generalization of an approximation to true FM, which we'll talk about next time, does have a time varying amplitude, okay, because of the SQ component, okay. But for beta small, which would appear in here, this is the amplitude variation is small. Then SQ squared is small compared to AC squared. Again, that's part of the narrowband FM approximation. Okay. Back to, let me write it over here. This will be back to tone modulation. Now, I've said that AM actually doesn't, or FM doesn't actually have this amplitude variation, but this narrowband FM generated by that system, which is not true FM actually, because it's based on this approximation that we made, does have amplitude variation. Okay. Back to tone modulation. So expanding an equation we had before, SFM of t is AC cosine of 2 pi fc of t plus 1/2 beta AC. And then here, did I still have that formula up here? Yeah, it's here. So again, using this trig identity for the products of the two signs, we get 1/2 beta AC cosine of 2 pi, then the sum frequency minus cosine 2 pi fc minus fm of t of the difference. Okay, the minus sign appears because it's the product of two sines instead of two cosines. And then when you take that difference, you get a 180-degree phase shift, which gives you the minus sign. But it's essentially the same trig identity. Okay. So if we looked at the spectrum of this now, we've got a component at FC that's has an amplitude of AC. I'm not drawing the negative frequency components. It would look just like this. This would be FC plus FM. We have another impulse at FC plus FM and a third impulse at FC minus FM. So this is the narrowband FM spectrum for the tone modulation case. Okay. Again, it's not true in general for that system used to generate narrowband FM. We would actually have our the integral of our message, the spectrum of the integral translated up around FC. Okay. How's the bandwidth of the integral of a message related to the bandwidth of a message? Well, in the frequency domain or the Laplace domain, to integrate, you just multiply by S or j omega. Okay. To differentiate, you divide by S or you divide by j omega. Okay. So if this is m of f, okay, because it's 0 out here, the bandwidth of the integral will be the same as the bandwidth of the message. Okay, so, because it's 0 outside the bandwidth. So there's no change there, and the integration doesn't increase the bandwidth or decrease the bandwidth. It's the same, neither does differentiation. So, but the point here is that the transmission bandwidth is 2 times our message frequency, which is the same as AM. Okay. So all of this, just to say that narrowband FM has the same bandwidth as AM radio. Matter of fact, the spectra looks very much like that of AM radio. Okay, we still have to, and this is not the general case, but it's an introduction to the general case. It's giving us some hope anyway that what we end up with is some sort of spectrum that's centered around the carrier frequency, and that will turn out to be true. Okay. So on Monday, we'll actually look at the spectrum of wideband FM. We won't use this approximation for small beta. We get into some Bessel functions, okay, which I don't know if you've seen those in any of your calculus classes. You have? No, you haven't seen them in calculus. Physics, okay. So we'll talk, but don't let that worry you. Okay, we'll then come up with an approximation for the bandwidth for FM. That's pretty simple. Okay, it's got this 2FM component, but then it's got another component based on delta F. Okay. So and this is, if you remember, I said initially the engineers thought, well, I can adjust the bandwidth so that by changing that KF so I can have a really small bandwidth. Well, in practice, they found out it could never be less than this. Okay, it could never be less than twice the frequency of your highest component in your signal. So FM can never have a bandwidth less than AM radio. Wideband FM, the bandwidth is actually greater than AM radio. But we'll talk more about that on Monday. So have a good weekend. That's it for today.